Welcome back to our series on advanced aircraft engine modeling. In this episode, we're going to take the steady state deck we have so far, add some simulated engine dynamics, and package everything in a nice class so that you can easily add to your simulation. Let's dive right in!
3, 2, 1, top.
3, 2, 1, half. The Flight Test Engineering channel.
First, I'd like to give you an update on the CF34deck v3 file that I uploaded to GitHub. I ran the same file that we had before, the same deck file with pyCycle, but now I included N1, which is the low pressure compressor RPM, and N2, which is the high pressure compressor RPM as well. This way we can know a parameter that is more akin to what we have in the cockpit. I also saved this file already cleaned up without the 19,000 feet anomaly that we detected on the last episode. We're recording this on June 2025 and we are running version, well, let's see here, pip freeze grep pyCycle. So you can see that we are running version 4.3.0 and hopefully in the near future the folks at pyCycle are going to be able to find out what's behind that anomaly and publish a new version. So keep an eye on the version so that you have the latest and greatest coming out of the pyCycle community. They're amazing. If you're trying to model the transients of a gas turbine, things get complicated really fast. To do that, you'd have to understand the rotor dynamics, either from the compressor and also from the turbine, and how it's affected by the combustion chamber as you add fuel incrementally and increase the temperature, and that affects the turbine and affects the compressor and so forth. And on top of that, you have to ensure all the flow compatibility, like we saw on the previous series that we had on jet engines, where you're going to have to check if the nozzles are choked, and if they are, you have to ensure that the mass flow is consistent between the turbine and compressor and all of the turbo machinery. So this would get very complicated very quickly, and it's beyond the scope of this channel. So we're not going to tackle the problem this way. We're going to tackle it in a more simplistic approach, and let's look into that. So instead, we need to look at a real N1 response from an engine. If you try to find online, it's going to be really hard, at least it is for me. So I found just a few plots, and this is one of them. I'll link the paper down below, but you can see that whenever you change throttle in your engine, the RPM is going to follow a certain curve. And what does that curve look like? Well, the RPM doesn't start immediately to go up. It takes a little bit of time. Then it rises sharply, and then it kind of stabilizes on the top, like this. So you first can think of this as a first order response, but then you lose this initial portion here. I have one more picture that we can have a look, and this is from a NASA paper way back then. Unfortunately, I don't have the original, but it's a very good example of what the engine response looks like. If you look at the engine rotational speed here, and here on the bottom graph you have time, you can see that this is 0.48 seconds and so forth. So the N1 rise curve looks like this, like an S curve. It rises slowly initially, then more steeply as you are in the middle, and then it kind of levels off smoothly when you get to the top, right? What kind of curve is this? What kind of mathematical function gives us this curve? Let's look at one that is very similar to this, and perhaps we can work out the timings to give us a pretty good simulation of what this curve looks like. The function I'm proposing to use is this logistic function, which has an S shape just like this, just like we looked at we could use, right? And the parameters that you can change on this function are three. You have L, K, and X0. Let's look at each one. L is what's called the carrying capacity, which is the top of the curve where it tends to. K is the logistic growth rate, which measures how steep is this portion of the curve. And x0 is the value of the function's midpoint. So you can shift left and right this midpoint here with by changing x0. So it's pretty good function to work with and try to adjust to our parameters. Let's see how we can do that. So here I created a simple notebook just to plot the function to see what it looks like. It's the function that we saw in Wikipedia, no difference. Here are the parameters. We start by importing the regular stuff, matplotlib and numpy, and then we just define the function here, taking into account L, K, and T0, right? And it just returns the exponential. And on this one, I just defined the plot of the function, easy, so that we can send the parameters and get the plot quickly, like in this one, right? And this is what I'm proposing. We know for sure that a civil engine needs to accelerate in 8 seconds. That's in the requirements. So we can try to figure out what are the parameters that would render this curve to reach its top at 8 seconds. This is what I try to do here by adjusting the parameters. In this case, we have k equals 1.1, t0 equals 4.5, and L equals 1. And L equals 1 is going to be important later. We're going to keep it all along because our thrust lever angle, TLA, is going to vary from 0 to 100%. And we're going to send a percent to our function, meaning it's going to go from 0 to 1. So that's why L equals 1 works for us, right? And then you can see pretty much here that it starts from 0, rises up, and reaches almost 100% N1, let's call it, or engine speed at 8 seconds, which is what we want. But if you remember the graph that I showed before, you see that for small engine variations, you are going to get a different response from the engine. Because in that sense, you don't have to wait for the engine to spool up and have all the transients in the low speed, which is where most of the problems are in terms of controls. And when you have small variations of throttle on your engine, typically the N1 rises much faster. So we can have another set of parameters here for our logistic function with k equals 2.1, T0 equals 1.5, which is much closer to the left, right? So it's going to rise up, and the midpoint is going to be much to the left, and still L equals 1. And here you can see that whenever you have small throttle angle changes, the engine is going to spool up really quickly, and it's going to stabilize in under 4 seconds. So we're going to play around in our simulation with these two set of parameters, and of course interpolate in between. Let's see how we do that. Right, so we are in the notebook here now, and we're going to do the standard imports again, pandas, numpy, matplotlib, but this time we're going to import as well time and time it. Time it we used in the last episode to time our API calls to see how many hertz we could get, and then random as well. You'll see why in a minute. And here we just set the style and everything like we had done before, so let's run that. And here we start with our Turbofan DAC class. So what is the main change that we had from the last episode? On the last episode, we defined functions to produce our DAC, right? And also to do our lookup table. In this case here, we're going to move all those functions inside the class. And the beauty of this is that now the class can keep track of all of the internal variables. So there are things that we had to calculate every time we called the function on the last episode that we're not going to have to anymore here, because since we can calculate those values when we instantiate the first object from the class, we don't have to calculate it anymore. And that's going to be very useful later when, for example, we need to know what are the Mach numbers that we have in our huge table, and we already had that calculated when we instantiated our object. So let's look into that. Well, the function here is going to take in our, just like we had in altitude, the Mach number and the thrust lever angle. Notice that now it's not a power percent that we had before. It's going to be the thrust lever angle, and we're going to have to convert from one to another. You'll see how. And we're going to use the logistic curve to simulate the engine response to make it real, let's say, in 8 seconds. Here is just a reminder to you what is the logistic formula, what are the parameters, and then we're going to say that the TLA is going to be mapped to the actual engine power percent, PC, which is then going to be used to interpolate from our deck and return the values from our engine. So that's the idea. You have a thrust lever angle that you change in the cockpit. That thrust lever angle is like a demand that you pass on to the function. That gets shaped by the logistic function to another value. This intermediate value is going to be changed or mapped into the PC percent value that the deck understands. And from that value, you get the engine parameters. That's the idea here. So what is this init function? This is run every time you instantiate a new object from this class, right? What are we going to pass into this function? Well, we're going to pass in the file name that we want to read the data for. This is going to be the table, the huge table that we calculated on the previous episodes, where you run pyCycle and generate all the off-design data points that you had. We're going to pass in the string. We're going to pass in an initial thrust lever angle, and if you don't pass anything, it's going to assume 0. We're going to pass in an initial time. Again, this is going to be assumed as 0 if you don't pass anything. And the idea here is that you're going to be able to run this on a variable time step, meaning that if you have your simulation running on the computer and the operating system is non-deterministic, meaning that you don't know how many times per second that function is going to run, given that you might have disk access or other things that the operating system is doing on the background, then you cannot rely on a fixed time step for your calculations, especially your integrator. So we're going to then keep track of time inside the class or inside this object to be able to return a true 8-second rise time for our engine, no matter how far apart are the calls to your function, okay? This is the idea. So we need to initialize the function with the initial time of the simulation. That's what initial time means. And here we're going to first define all of the logistic parameter functions. Remember, we have two shapes of the logistics function that we want to go for. One is for small thrust lever angle changes, and the other one is for large thrust lever angle changes. For small TLA changes, you want a short, fast response. For large TLA changes, you want the long 8-second response. So we're going to define here a window start thrust lever angle. It's the baseline for our logistic curve. We're going to set the target TLA. It's where we want to end. In this case, for example, we would be going from idle to toga power. We also define a variable here called window start time, which is the time that we are going to start computing the window for the logistic function. The current time is going to keep track what is the current time that we are calculating. L, which is the carrying capacity that we talked about, is going to be fixed at 1. And here we have two sets of values, T0 long and K long, and T0 short and K short, which are the values that we saw in the curve before to give you a fast and a slow response for your engine. The delta TLA long and delta DTLA short are the thresholds that we're going to use, meaning that if you have a thrust lever angle change of 0.15 or 15% or less, we're going to choose the fast response. If you have in between 0.15 and 0.4, meaning from 15% to 40% difference between the current thrust lever angle and what you desire for, we're going to interpolate in between. In more than 40%, we're going to go for the long response, meaning that the engine is going to take 8 seconds to go from the current power to the power that you are desiring. And here we start with the beauty of objects in Python or any other language. We can calculate the slopes of the curves that we're going to interpolate between the fast and slow responses and already keep it. We don't have to calculate this every time we call the function. So we calculate the K slope and intercept and the T0 slope and intercept, classic way, and just store them on this variable. And then we keep track of what is the current value for K and what is the current value for T0 in these two variables here. So just a quick recap, these are all the variables that are going to be linked to our logistic function calculation. Okay? Moving on, for the next part of our init function, we're going to read in the deck that we calculated on the previous episodes. So we pass in the input file, okay, and then we try here and accept, meaning that if you fail to read the file, we're going to print out some messages. So first, we try to read in the CSV file via pandas, so we create our data frame, just like we saw before. And here I just left a remark. If you still have the file that has the 19,000 bug included, you can just uncomment this line here, and this will filter out that data, again, like we did before. And then we're going to have a few messages here if we can't find the file. First, if we can't find the file, the error is going to be a file not found, and we're going to return this message. The file X was not found. If it was empty, we're going to say that it's empty. And then if you cannot parse the file because you gave it a name and it is a valid name, but pandas for some reason cannot read it, it's going to give you this error message that the file cannot be parsed. And even then, if your error is not one of these three, it's going to give you an unexpected error message stating what happened. Okay, moving on with our init file. Here is where I moved a few of the calculating lines from the functions that we had in the last episode for our lookup table into the init. So for instance, here you're going to recognize that we create a list of the unique altitudes from the file that we just read into this database. And we're going to do the same thing for the Mach numbers that we had and the percent, the PCs that we had on our deck. These lines here are going to filter our data frames and give us just a list or a dictionary, depending on which one, of the values that we can choose to interpolate at. This one here is going to just store in the column names whatever names we gave to our deck, right? Whatever variables we have in our deck. And at this point, we finished the init. We're going to see it, the first internal function that we have in our class. Every time I put an underscore before the function name, it means that it should be an internal function. It should not be called from outside of the class, of the object. So in this one, we're going to get the dynamic response from a thrust lever angle demand. You're in the cockpit. You have your TLA set at one point. You change the TLA. This is the number that's going to get into the function. First, we're going to calculate the delta here, the DTLA, which is going to be the difference between whatever you're demanding from the engine, the input that you just gave to the function, and the current target that we have in our logistic function window. And here is where we're going to choose which parameters we're going to use for our function. If your DTLA is longer than the DTLA long that we defined, then we're going to use the long parameters for our logistic function. Vice versa, if it's shorter than the short values that we define, you're going to get the short values for our function, short parameters. And if it's in between, then it's going to get an interpolated value for K and T0. And we just return K and T0 to wherever we have the response. This is the next function then that's going to shape your TLA response according to the logistic function. So you're passing in a time and a TLA demand, just like we saw. And what are we going to have here? If the TLA demand, meaning what you're passing into the function, is whatever it is already set as the target TLA for the window, then that means that we're not changing our thrust lever angle. We're just calculating we're shaping the response. We're changing what is the TLA response according to that logistic function. So we calculate the DT, the difference in time between what we have right now and the window start time. And here's where we're going to return the logistic shaping. If our dt equals less than 10 seconds, and more than 0, we're going to calculate here the logistic function return value, considering whatever delta time we have from the beginning of the window, the parameters that we have calculated already, if we are in the low, short, fast, or in between in the interpolated values. And we're going to shift our value to have the 0 instead of 0 and 1 instead of 1. We're going to have the 0 shifted to the bottom of our target window and the top to the top of the target window, meaning that we're going to move that curve, the S curve, to wherever TLA window we want. Okay, so, and if we're not in these conditions, meaning time less than 10 and more than 0, and time is more than 0, it means that we have passed our window for our logistic function. And then, in that case, we're going to say that our target TLA is the current window target, because it hasn't moved. And the window start TLA is going to be window target TLA, meaning that we are at the end of the window and everything is equal. And we're going to just return the current TLA. If we have changed our demand, then we're going to start the window start time to t, which is the time that we received this information in the function. We set the window start TLA as the current one, meaning that we start from where we are. We recalculate our K and T0, and we set the window target TLA as the current demand. So suppose you're coming in from a TLA of 50% and you're going into 60%. This is how you set your parameters for the next round of calculation. This next function here is going to map whatever TLA we have to the PC window that we have in our deck. And we're going to map and say that TLA ranges from 0, which is going to be our idle, to 1, which is going to be our takeoff go-around thrust. And this is going to be mapped to a PC that's going to be idle, and I'm going to touch this in just a while. To PC1 is going to be toga, takeoff go-around power. And why are we changing the idle value? Because if you look at a real aircraft engine, the idle value changes with altitude, meaning that as the higher you are, the higher the idle value is. And why do we have this variation? Because with altitude, it gets more complicated to control the engine, and you don't care as much for a low value of idle, because you can use the speed brakes, for example. And at low altitude, the value of idle is bound by the 8 seconds required to accelerate the engine to take off go-around power from the regulations. We're going to set idle as 0.55%, which is our minimum PC that we have in our deck, and that's going to be at sea level, and that's going to increase with altitude. So then we just return a TLA times 1.0 minus idle plus idle. So linear interpolation between these values that we have here. And here's our nice table that links idle value to altitude. We say that if you have lower than 3,000 feet altitude, you just return 0.55. Between 3 and 5, 0.58. 5 and 8, 0.6, and so forth. These were chosen as a guess. You would need to check what would be the idle value for your engine to create this table here. I just created one that looks like something real, but it's not. It's just a guess, okay? And here we start with the same functions that we had on the previous episode. I'm not going to explain them again because we went through them in details in the last episode, so you can look at that video if you want to understand how it works. But here we have the get bracket function, we have the linear interpolation function, the adjust limits function, and our main interpolate altitude, Mach, and PC functions. They're all the same. The only difference you're going to see is that we don't have to calculate the list of Mach and altitude and PCs again. We just use the same list that we calculated when we had the init of our object. Okay. And here we have the function that's going to really interface with the object. I gave it a name run deck, and what do you give it? You give it your altitude, your Mach number, your thrust lever angle, and your current time. So the idea here is that you have a simulation running, calculating the 6 degrees of freedom model, for example, and every so often you call the deck, say, okay, my thrust lever angle is such. You call this run deck method on your object, and it's going to run and give back to you whatever engine parameters we have. Given these inputs, it's going to interpolate the deck data, and using the fake TLA that we talked about with the logistic function, give you the deck parameters. So it's a simple call. We first calculate the idle PC given the altitude. Then we calculate our temporary TLA response, meaning we shape our TLA according to our logistic function. Then we transform our TLA into PC by get PC from TLA, and we call our interpolate function that we saw before on our previous episode with altitude, Mach, and PC this time, and return that dictionary. We're going to first start the time of our simulation. And here we are going to use the performance counter from Python, which is a clock that is monotonic, meaning it's always going to be rising. And it's the best one that we have in terms of precision. And my idea here is that you would be running your 6 degrees of freedom with the same performance counter time. And then every time that you want to know what the engine response is, you call this function that we're going to look now. So first we record the initial time of our simulation. And then we instantiate our class into this object. We're going to call it CF34-10 E5A1. We call our Turbofan class with the file name for our deck. The initial TLA, we're going to start at 0. And the initial time is the time that we just stored here. So now we have it already initialized. And then we can run a few tests here. For example, we can set the altitude at 35,000 feet, Mach number at 0.82, start with our TLA. And let's record three states here. First, let's record the throttle values, the TLA that we are going to input. Let's record the power percent that the deck is going to be receiving from our shaped function, and then record the thrust that the deck gives back. So we start a time vector, and we do 1,000 calculations here. So we call the deck function, like we saw, run deck, with a given altitude, Mach number, TLA, and our time, current time. And when we get back the engine state, and we just append our lists. So we append the TLA, thrust, net thrust that we have from our state, and the PC that we passed into our deck. And we update our time vector as well with the performance timer minus the initial time, so that we have a nice plot later. Instead of a big number, we have just something starting from 0. And here we just print something on the screen every time we have 100 calls, just to see that the function is running. And here we're going to add the TLA variations. So when the index is more than 100, TLA is going to jump to 0.5. More than 200, 0.85. So here you can see the step that we're going to create for the TLA, trying to see a fast and a slow response. Like from here is going to be slow. You have toga power going to idle. And here again, slow, from idle to 0.9. But here it should be quick, a fast response, going from 0.85 to 1. Here we're going to make the simulation more realistic by introducing a random time delay between function calls. This is what we're doing, right? We're creating a random time delay between 0.1 and 0.19 seconds. And we're going to just tell it to sleep. And at the end, we print end of line here. So let's run this. It's going to take a while, so I'm going to speed up the video here. Okay, we're back. And now we can just plot whatever we got. So we create a figure here, and we're going to plot the TLA, the PC, and the thrust. Let's see what we get. Nice. Let me just zoom out a little bit. There you go. Here we can see the TLA going from idle to halfway, 0.5, and then so forth in the stepwise. Here is the shaped response that we get from our logistic function. You can see that the curves are really nice here. And this is the deck response for thrust. You can see the variation is going not so sharp as you would get if you didn't have this shaping function, but it resembles pretty much what you would get in flight. Okay? So this is a pretty good and simple way to simulate your engine dynamics. I know this can be improved, and if you have any other ideas, it would be great to hear from you. Right, so last thing that I wanted to do on this video is going to be a speed check. It's the same code we had before. We're going to use the timeit library to run 1,000 calls to our function. That's what we're going to do. We're going to use our object and then we run deck. So let's see how this goes. How much are you going to guess that we are going to improve in speed? We had roughly 20 Hertz last time. Let's see how much we get now. It's the same computer running the code, so nothing changed except the function that we have here. Remember that we had an optimization by adding those calls or those calculations of the altitudes and Mach numbers to the init only. So we don't have to calculate that every time. There you go. So we're up from 20 to 30 Hertz. It's a significant improvement in our speed. So that's it. I'm happy with that. And this brings us to the end of this series. We learned how to use pyCycle to create our own deck, and then we created our lookup table scheme to interpolate the data and give us a fast responding function, but still in static conditions. And in this video, we added some dynamic response via input shaping and package everything into a nice class that you can easily integrate into your own simulation code. Thank you for being with me on this Turbofan journey, and see you in the next series.